And then fission and fusion reactions. So here goes. So artificial transmutation, which sounds like we're doing a lot of something really weird or mutating things, is basically just changing an element by bombarding it with high energy particles. Artificial elements as well as isotopes are ones that are not normally found in nature. 1919, Rutherford was the first scientist to artificially transmute an elephant. Not an elephant, an element. We're bringing biology into this apparently. In his experiment, he bombarded stable nitrogen-14 with alpha particles. So we're firing an alpha particle at a nitrogen-14 atom, and as a result, he temporarily made fluorine-18. Due to the weak nuclear force, the fluorine-18 nucleus immediately decays and emits a proton. The resulting daughter nucleus was oxygen-17, and this was the first artificially transmuted isotope. So one of the things to remember here is you get all kinds of interesting reactions that happen in these processes. We can keep track of them using balanced nuclear equations, though. So let's take a quick peek here. Alpha particle and the nitrogen-14 nucleus are both reactants, so that means they're both on the left side of the equation. And then in terms of what do we make, well, 14 plus 4 is 18. 7 plus 2 is 9. And if we look on our periodic table to see what number 9 is, that is fluorine. Right, so that's going to be the thing that is originally made. So that's kind of our prediction. Now, in the end, we know that that's not actually what was made. So I can make this prediction, but that's kind of like my intermediate step. So what's actually going to happen, we know we end up getting a proton out of this. Okay, so again, our atomic number is 1, and the nucleon number is also 1. And conservation of nucleon number says that there is 18 here, which means I need to have 18 over here. So this is going to be a 17. Conservation of charge says there's 9 here, which means over here I have to have another 9. So 1 plus 8 would be 9. And voila, we have oxygen 17. Because oxygen is the thing that has 8 protons. Normally, okay, you can see I wrote in this intermediate. Normally, you don't have to write the intermediate unless it's asking for every step. Normally, it's going to be, here's what we started with, here's what we end up with. You're generally going to be told enough reaction information that you don't have to say, oh, wow, 14 plus 4 is 18, 7 plus 2 is 9, and away we go. This is, the real story of what happened, but you generally don't need to include the intermediate unless, again, you're asked for every step along the way. All right, and again, conservation of nucleon number, that's making sure the top numbers are balanced. Conservation of charge means that the number of protons at the bottom are also balanced. After this, scientists tried to create new elements using particle accelerators, discussed later in the unit. All elements beyond uranium are artificial. None of them are stable. So everything from neptunium on is not something that is found naturally in nature. We call these things transuranic, as in they're beyond uranium. So transuranic elements are all artificial and therefore radioactive. Some have longer half-lives than others. So let's look at an example. Einsteinium-253 is bombarded by a particle. As a result, Mendelevium-256 is artificially created and a neutron is emitted. Determine the identity of the unknown particle. So here we need to find Einsteinium and we need to find Mendelevium. You're going to need your periodic table for this. And basically you want to try this on your own, and then so you can pause the video and then give it a try. So Einsteinium, which is one of those ones that for whatever weird reason I just know, even though my computer is being uncooperative right now. Hello. There we go. So Einsteinium, I know, is element number 99. I'm told in the question that the isotope is Einsteinium-253, which means there are 253 nucleons, plus something is bombarded by a particle, gives me Mendelevium (256). Oops. And I will grab my periodic table. Make sure that I actually do this right. Yes, I was correct. I apologize for my squeaky chair. All right. So Mendelevium has 101 protons. It has 256 neutrons. Sorry, 256 nucleons, my apologies. And then we also make a neutron. That's where that word came from. If I look here, conservation of nucleon number is going to be 256 plus 1, which means over here, I need to have the same thing, 257. So 253 plus 4 gives me that. And note that I have to have the same conservation of charge going on as well. So I've got 101 plus 0, so 101 on the right-hand side, which means I need 101 on the left-hand side. 99 plus 2 gives me that. What do I know of that has 4 and 2? And indeed, it is an alpha particle. So Einsteinium 99 is bombarded with an alpha particle, and we make Mendelevium 101. Sorry, Mendelevium 256 with that 101 protons, and a neutron is emitted. Okay. And you can kind of see everything going on right here. If you were to say, if this is like the short answer and you said helium-4, I would have to say that that was fine. Generally, it is going to be an alpha particle, just because that's normally what we use. Creating those transuranic elements, actually bombarding with alpha particles or with protons, is fairly common. Alpha particles are a little bit more common than just protons because you're adding neutrons and protons then. And that tends to keep the newly created nuclei more stable. Also, accelerating a alpha particle to the right speed to cause this reaction to occur takes less energy than, say, like I could probably say, oh, wow, let's see here. I want to make element number 101. Well, let's take element 56 and 51 and 50. The problem is, if I'm trying to accelerate tin, element 50, and antimony, element 51, compared to an alpha particle, these are heavy. So getting them moving fast enough actually takes a great deal more energy. So it's easier to have a stationary Einsteinium and smack into it with an alpha particle than to have two much heavier elements trying to collide with each other. Anyways, Enrico Fermi in 1938 discovered the first fission reaction, which is when a large nucleus splits into two smaller nuclei. Normally, to trigger a fission reaction, a slow-moving neutron enters into a large nucleus, such as uranium-235, which, if you think about it, initially is going to then make uranium-236. Since it has no charge, there is no extra repulsion. But what we've done when it enters slowly, the weak nuclear force becomes significant enough that it causes the uranium-235 to become unstable. If the neutron moves through the nucleus just too quickly, it actually doesn't have any effect. The instability is overcome and as the neutron leaves. In the case of uranium-235, the nucleus then would split into two smaller daughter nuclei. In this case, barium-141 and krypton-92. This is called nuclear fission. Now, do you have to be able to predict these? No. But if I gave you one, you should be able to predict the other. There will be a loss in mass. This is called the mass defect. And this mass is converted into energy. And this is the energy that is liberated in fission reactors, as well as atomic bombs. So let's consider how this fission reaction is illustrated using a balanced nuclear equation. So same thing again. What do we got going on? Well, we've got uranium-235 and a neutron. And again, this neutron for this reaction to happen has to be moving slowly, but it is a reactant, so we leave it on the left-hand side. These daughter nuclei that are created, usually they are radioactive. Now, in this case, you were told it's barium-141 and krypton-92. You might not always be told both of them, but if you're going to predict them, you would have to be at least told one of them. What you should hopefully notice, 36 plus 56 does equal 92. Now, if you're paying attention and doing the math, what you're going to see is that if I go 235 plus 1, that is 236. And if I go 141 plus 92, that's 233. So this isn't it. There's got to be something else. And in fact, in the case of a fission reaction with uranium, we also liberate 3 neutrons. The cool thing about these neutrons is that if we can get them moving slow enough or at the right speed, this one step here, which required one of these, can lead to 3 more neutrons. And each of these 3 could cause another uranium-235 to react. So we release energy at this step, and now we're going to release triple the energy at the next step, triple it again, and you can see how this gets very big very quickly. These neutrons actually carry energy from the mass defect in the form of kinetic energy. Also note that a gamma photon might be emitted in this reaction. Okay. Top numbers will be conservation of nucleon, right? 235 plus 1 is 236. 141 plus 92 is 233. Plus 3 more here is 236. And the charge at the bottom has to remain at 92. And this, yeah, as I was describing before, these 3 extra neutrons can bombard more uranium nuclei, causing more fission reactions, and this is a chain reaction. And here we've got an illustration of it. We've got basically a pretty picture of the uranium-235 nucleus. We've got the neutron coming in, lots of energy released, 3 more neutrons, 2. So here's our parent nucleus. Here are our daughter nuclei. And away we go. Now you can see in terms of like a chain reaction, right? Well, here we've got 1 parent nucleus. Computer being slow. Try again. There we go. Splitting into 2 daughter nuclei, sorry. This 1 neutron causes another reaction. You can quite easily imagine this neutron causing another reaction. This neutron causing another one, assuming they're moving slow enough, of course. Right? Here's another way. Right? This is the other kind of question I was telling you about. Right? We can look at our uranium-235 bombarded by a slow-moving neutron. Lovely. Splits into 2 smaller nuclei, one of which is zirconium-96. So let's give this a try. Uranium-235. You will learn that uranium's number of protons is 92. Plus a neutron, okay, those are my reactants, is going to make zirconium-92. So I'm going to have to find zirconium on my periodic table. And it is going to have the atomic number of 40, which means I have 40 protons. And if I'm told in the question that it's zirconium-96. All right. Now I am going to get 3 neutrons on the other side here. So let's first figure out what element I'm getting as my other element. So I've got 40 plus something has to give me 92, or I can go 92 minus 40, and so that's going to be 52. So I find element number 52, which is tellurium. Tellurium, and it is got a 52 down here. Now, to do a little bit of work here, I have 3 neutrons. So I'm going to write those in there before we try to get to finding our isotope of tellurium. A little bit of math we have to do here, because I've got, in terms of conservation of charge, I've got this figured out. 92 and on the left, sorry, and 92 on the right. However, I have 236 on the left for nucleons, and 96 plus 3 more, which is 99, on the right. So I need more, which I'm going to get them from my isotope of tellurium, but I need to figure out which one it is. So I figure out, well, I've got 236 on the left side. And I need to have the same number on the right side. And so essentially, if you think about this algebraically, 236 is equal to 96. This is like grade 7 algebra, really. 96, that is supposed to be a 6. Yikes. Plus x plus 3. And solving this, of course, 236 minus 96, and then subtract 3. So let's do that. Oops. And that tells me this is going to be tellurium-137. Lovely. Okay. And again, you could also do this conservation of nucleon number first. Fair enough. Bottom numbers have to obey conservation of charge. Daughter nucleus here, the one that we don't know, has got a 52, which is tellurium. And there we go. All right, so you sort of have the information required now to at least understand the theory behind a nuclear reactor. A lot of the control mechanisms are tricky. And in addition to them being tricky, the technology that's required to make it all work is definitely well beyond the scope of this course. In the reactor core, we have a bunch of fuel rods, and they are enriched fuel rods, which means they have a higher concentration of uranium-235 than would ordinarily be dug out of the ground. Right? Basically, we've taken some way of enriching them. Now, you could use a mass spectrometer like we talked about yesterday. Usually, it's some form of a centrifuge to enrich that uranium, where similar ideas, we're using the different masses of the various uranium isotopes to separate out just the 235. Anyways, we've got our fuel rods, lots of uranium-235. And fission begins naturally when a slow-moving neutron, with a slow-moving neutron. And the uranium-235 splits into two smaller nuclei inside of the fuel rods. The daughter nuclei are also radioactive. The energy created by fission is transferred to the emitted neutrons as kinetic energy. Now, if they continue to move at high speeds, a chain reaction actually can't occur. So we need to do something to slow them down. How do we slow them down? We use heavy water. Now, you might think, okay, heavy water, that seems weird. Really, with heavy water, what we're using is quote-unquote heavy hydrogen or deuterium. So normal water, which is like 99% of the water that we'd find in the ocean or something like that, or even more, is H2O. And each of the hydrogens has just one proton. There's no neutrons. But in our heavy water here is deuterium. So hydrogen with one proton, obviously, otherwise it's not hydrogen, and one neutron. So we would write this as hydrogen 2 or this. Right? So that's in terms of the hydrogen. If I'm writing it in isotope notation, that's what I'm using. And I'm using each of these hydrogens in this chemical formation with water. All right, does that make sense? What this does, they have an additional neutron. And heavy water, they call it a moderator. It tends to slow down the neutrons. Now, it also heats up because those additional neutrons make the water heavier and more likely to be hit by the emitted neutrons. Okay, this heavy water starts to heat up. To ensure the water doesn't turn into steam too quickly, the heavy water in this chamber is placed under high pressure. In this way, we can heat it to well over 300 degrees Celsius since it still doesn't evaporate. This water is now what we call superheated. Okay, so it's liquid at 300 some degrees Celsius. Logically, the heat must be removed or the area will become dangerously hot. If we don't remove it, eventually something bad is going to happen. Because if you think about it, if water is under pressure, and then we start to boil the water, now the pressure is going to increase dramatically because liquid water doesn't take up nearly as much space as steam. So in terms of how this reactor works, we pump the primary water, this heavy water, away from the reactor core. And it goes through a loop, and its heat is transferred to what they call secondary water. This, by the way, this secondary water here coming in, it is regular water. It is never actually exposed to anything directly that's in here. So this heavy water that we've got down here goes through this loop. It heats up the secondary water, but it heats it up not by mixing with it, but by just going through basically metal loops inside of it. So we're heating the water, turning it into steam. It's under low pressure, so it boils at 100. Now the steam goes away, and this steam is actually used to turn a turbine and generate electricity. Right? And the electricity then is transmitted along the power lines. And we have a third source of water, usually a lake or something like that. And this lake actually, or external water supply, is then used to cool. So we've got steam. There it comes. Steam turns the turbine. And we've got a third loop of water pipes that's external to the reactor, where we're pumping in water at like 25 degrees Celsius, 20 degrees Celsius, and it's going to cool the steam back down to water. Water then gets pumped. This is our secondary water, gets reheated, and this water just loops around. So we've got heavy water going through a loop, we've got secondary water going through a loop, and we have cooling water going through a loop. None of these samples of water, if all goes well, is supposed to ever come into contact with each other. These pipes are all supposed to be sealed, and so we never have this water that's on the outside ever in contact with anything radioactive. Assuming all goes well. Control of nuclear fission is essential if, as we have learned in history, if fission goes out of control, it can lead to meltdowns. You might have heard of 3 Mile Island in Pennsylvania or Chernobyl in modern-day Ukraine. Both of those had bad things happen. Chernobyl quite a bit worse than 3 Mile Island. And now Chernobyl with military conflict in that area, other problems associated with that. How do we control the fission reactions? Since the fuel rods are enriched, then all of the U-235 atoms are very near to each other. Also, the heavy water keeps the neutrons moving slowly. This means that a chain reaction is relatively easy to accomplish. And you can see all kinds of good stuff happening here. We've got all kinds of these blue things are our uranium nuclei. The orangey colored things are our neutrons, 3 being released each time, and these yellow colored things are the daughter nuclei. All right, and this is a chain reaction. Lots of the neutrons actually get used to start new reactions, right? And obviously I can't draw this all, it's an exponential increase, but 1, 3, 9, 27, and so on. Process could grow exponentially. And if more neutrons are emitted than are being lost or absorbed, we see the process has gone critical. Means the fission will continue on its own without any assistance. That is, the nuclear reactor is working. Lovely. So some of them will get lost. So theoretically, right, it's a 1, 3, 9, 27, 81, and so on. In reality, some of these neutrons hit the walls. Some of them go straight on through our uranium and never actually do anything. However, as the reaction proceeds, we've got more and more fission happening, and now this is going to mean that we could have something bad go on. How do we slow it down? Because if it heats up too fast, we get an explosion, and this is not good. We use control rods. Typically, these are made of boron and cadmium, which both have the unique ability to absorb neutrons. as we insert the control rods, they absorb neutrons and slow the reaction down. All right. So as the control rods go further in, they absorb more neutrons and slow the reaction down, basically keeping it at a relatively sane pace. Fission reactions are easy to start. All we require is a slow-moving neutron. We get a ton of energy. Comparatively, a kilogram of uranium compared to a kilogram of coal, that kilogram of uranium gives us, give or take, 2 million times more energy than 1 kilogram of coal. And this is because the energy is coming from the mass defect rather than chemical bonds being broken. And the mass defect just gives us far more energy. Now, fission reactions have problems. Our spent rods, it's not like they've stopped being radioactive. They are full of radioactive material. How do we dispose of them? Some of them are going to be radioactive for thousands, tens of thousands of years. So what do we do with them? Well, first, the fuel rods are bathed in water to cool them. So they're stored in what looks sort of like, swimming pools. I read a what if kind of story about, like, could you swim in that pool? And apparently, yes, divers do all the time to service the rods. However, could a random person from the public swim in that pool? No, those pools are rather well guarded because of what's in them. Also, if you'd swim near the surface, you'd be fine. If you were swimming right at the bottom near the radioactive stuff, you might be okay because they're sealed in glass and things like that, but probably a bad idea to try it. Now, this does contaminate the water. Then we got to dispose of the water. Finally, we put the cooled fuel rods in thick cement, thick enough to protect everybody around us from gamma radiation. So they're now no longer emitting that gamma radiation. It's all stuck inside the cement, which will block it. And then we often bury them deep underground, old mine shafts. And in this way, radiation doesn't reach the surface in high quantities. Another disadvantage, uranium is a non-renewable resource. Some scientists have estimated that uranium deposits will only last 200 years, maybe a bit more. Now, should be noticed that if we change the way we use it, it could last many thousands of years. Currently, the way most of the time we use it, it doesn't last all that long. Now, how do we increase the efficiency of fission reactors? Right? Could we reuse these fuel rods in some kind of a different reactor? Problem is, these kind of studies are expensive, and government regulations actually don't allow most scientists to do this. And it's not just necessarily like Canadian government or American government. It's ideas like non-proliferation. Because some of these types of experiments could also be used to create weapons or weapons-grade radioactive materials. And so people are nervous when people start doing experimental nuclear reactor stuff. Sometimes with good reason, sometimes not as much. Additionally, uranium could be extracted from seawater. It's estimated there's about 4.5 billion metric tons of uranium in the oceans. That'll be about a 60,000 year supply. Doing pretty good there. We have also the technology to make what are called fast breeder reactors, which can make more fuel than they actually use. So these are reactors that are designed to make fuel, but not necessarily energy. These reactors could make supplies to last the next additional 30,000 years, but current regulations don't allow this to be done. We are concerned about countries using these to make weapons-grade plutonium, as in let's make a nuclear weapon or stuff to make a nuclear weapon. So anytime you see somebody talking about fast breeder reactors, they're making fuel, they're making radioactive stuff that we could use to power other reactors. The problem is, what are you going to use that fuel for? This takes us on to fusion reactions. Fusion reaction occurs when small nuclei fuse or merge to form a larger nucleus. Now, naturally, this is what's happening in the sun. And this is typically what's going on in the sun, in fact. Deuterium, oh, there it is again, hydrogen-2, and tritium, hydrogen-3. All right. These two are going to, if we have enough energy, smack together, and we will make something bigger. Now, in order to fuse them, we must get them close enough together so that the strong nuclear force comes to dominate. Now, given that we have a positive charge here and a positive charge here, initially they don't want to do that. So we have to get them within 10 to the negative 15 meters, or 1 femtometer, of each other. Problem is, they repel each other. The closer they get, the stronger the repulsion force. But eventually you get close enough and suddenly the strong nuclear force takes over. And that's what we want to have. So we have to have them moving at high speeds to overcome that. To make particles move at high speeds, usually temperatures. Temperature of the reactants needs to be over about 100 million degrees. So this is not, you don't have any danger that your oven at home is going to start a fusion reaction or a fission reaction, just accidentally. Okay, it's just not hot enough. Now, you can probably see right away when these two isotopes fuse together, they create a larger helium-4 atom in a fusion reaction. And if you're counting, you're like, wait a minute, 1, 2, 3, 4, 5. 1, 2, 3, 4. There's a problem. And yes, you're right, there is a problem. So if this reaction occurs, we also are producing an extra neutron. Lovely. And then the neutron is emitted at fairly high energy, and the helium-4 also emitted at fairly high energy. I apologize for my dishwasher, which is demanding my attention. It says it's done and I should do something with it. Anyways, moving along. That energy, by the way, comes from the mass defect. Right? So, in other words, if I take the mass of this and the mass of this, compared to the mass of these two things, this mass is slightly more, which means we're releasing energy as helium-4 is made. Okay, here's our picture, slightly nicer than the little drawing that you had last slide. You can take a look at these. We'll look at some of the one or two of these on Monday, just some of the early atomic footage of some of the interesting things going on, but that'll be a Monday project. Now, let's consider how this, you need to change this. This should say fusion. Consider how this fusion reaction is illustrated using a balanced nuclear equation. So, these are the reactants, hydrogen-2 and hydrogen-3. Now, note that we know that helium-4 is formed. So, it's larger than either of these two. Tells us it is fusion. And if you look here, 1 plus 1 is 2. 2 plus 3, we've got 5 here. We need something else here. So, there's also going to be a neutron released. So the top numbers obey conservation of nucleon number. bottom numbers, conservation of charge, neutron is emitted. Note, this is not radioactive. This is not radioactive. Generally, no gamma rays are given off. It's possible, but fairly unlikely that too many gamma rays are emitted. It is possible, though, but I say not too many are given off. Very little radiation formed in this reaction. Now, granted, these two do have kinetic energy, so if they hit stuff, they can cause damage. But if we're containing them, this is a great source of energy if we could manage to harness it here on Earth. All right, so let's take a look. For this fusion reaction, find the daughter nucleus, and then using the masses given, find the energy liberated in the reaction in mega electron volts. All right, so if we look here, we've got helium-3. Now I'm telling you that this thing here has this mass. All right. And away we go. Let's take a look at it step by step. So first of all, we got to write this out. Okay, so this is a different reaction, right? This is tritium plus tritium. No, my apologies, this is not tritium plus tritium. This is helium-3 plus helium-3. All right. Double check that yes, helium-3, I need to learn how to read apparently. Helium-3 plus helium-3. Now, part of what we're making is a couple of protons. Okay, these are hydrogen-1 or protons. But something else is going to get made here as well. Total mass on the top is going to be 6, so nucleon number is conserved. There are 2 protons. Lovely, there we go. Total charge has to be 4. So the daughter nucleus is a helium-4. So it's some kind of fusion-y thing, because this is technically bigger than either of these. Right? It has an extra neutron in the nucleus. If we want to find the mass defect, I should actually go back to one of the slides that we had here, because I just remembered that there's an issue. This is the issue. You should change that. 1.66 times 10 to the negative 27. Continuing back to where we were. So maybe, there we go. So we have 2 helium-3s. So that means the mass of our initial reactants is going to be 2 times, this is, you were given these numbers, 2 times 3.01603 atomic mass units each. So a grand total of this many atomic mass units. Okay, turn it to kilograms. Lovely. There we go. Moving along. And here we go. Mass of helium-4 plus, so MT, mass total final. Okay, helium-4 plus 2 times the mass of hydrogen-1. There we are, 6.01994 U's. Again, multiply by 1.66 times 10 to the negative 27. That many kilograms. Note that we've got 10 to the negative 1.00132 times 10 to the negative 26 initially. That's our total mass initially. And slightly less after the fact. So mass defect, we're going to just subtract those 2 numbers. And punching that into your calculator, what you're going to see, I'm just double checking my math here. I am going to see this is not going to have a negative in front of it. It will be positive. And it's going to be 2.00996 times 10 to the negative 29 kilograms. And that means that many kilograms were converted into energy. So we find the energy liberated. That many joules, right? E equals mc squared, or delta mc squared. Lovely. Convert that into electron volts. Right, so essentially I'm multiplying by 1 over 1.6 times 10 to the negative 19 joules, or dividing by 1.6 times 10 to the negative 19 joules, which then gives me this many electron volts. This is times 10 to the 7, and if I want to change that into mega electron volts, I divide by 10 to the 6th, and it's 11.3 mega electron volts, which I can deal with I can kind of imagine 11.3 of something. This is just an arbitrarily large number, so this makes life easier for me to figure out. So, if I go back to this fusion reaction that we started with, oops, here we are. One of the things here is that we are getting 11.3 mega electron volts of energy from just 2 atoms fusing. Now, if we do this on scale with kilograms or tens of kilograms worth of atoms fusing, we get a lot of energy. Why would this be a good thing? Well, reason one, these things have stable, safe byproducts. Fission reactions definitely have radioactive byproducts, lots of radioactive waste. Fusion leads to stable byproducts, which makes it far cleaner. Now, those neutrons, I kind of skated over them. If they keep bombarding stuff around them, they can make it radioactive over time. So it's not perfect, but it's definitely not going to have the same amount of radioactive waste that we'd have if we were dealing with a fission reactor. Lots of fuel. Deuterium, so hydrogen 2, we can extract that from water. Lots of water on the Earth, especially in the seawater. So it's just about an inexhaustible supply. Now, that being said, what about tritium? There's calculated about 25 pounds worth of tritium naturally on Earth, but we can make it artificially by bombarding lithium with hydrogen. Lithium is abundant in the Earth's crust. It lasts for a long time. More energy is released per nucleon than fission. So fission creates more energy per nucleus. Fusion creates more energy per nucleon. Right? This has got 236, 235 nucleons. Becomes 236. Lots of energy out of that one nucleus. Here, we've got a grand total of 5 nucleons, and we're getting a good bit of energy, but per nucleon, we get way more energy here, even though the nucleus here is much bigger, so we get more energy from each nucleus. Per kilogram, fusion wins. Now, here is some disadvantages. And this is problems people are still working to solve. It is nearly impossible to maintain the 100 million degrees temperature that the fusion requires. Up to this point, we have not been able to create a self-sustained fusion reaction. At this time, we have two kinds of processes. We can try magnetic confinement or inertial confinement, and neither approach has led to self-sustained. This should say fusion. You got to change that. Neither of these would lead to a sustained fission reaction either, but that's not what we're trying for. So, magnetic confinement in this reactor, hydrogen isotopes move at high speeds and are converted to plasma or charged gas. Because it's charged, we can contain it in a magnetic field. We can heat that further by a neutral particle beam as well as microwaves. And we get this nice sphere of rotating plasma, which keeps everything nice and hot. We surround it with a vacuum chamber to help keep the heat from conducting away. Up to this point, the problem is we are putting more energy in terms of all of the making these magnets work than we get out. And then we can't maintain the temperature long enough to make it self-sustaining. We can also have inertial confinement. In this way, we've got hydrogen isotopes held at rest in the center of the fusion core. Hydrogen is blasted by lasers from all directions, heating it up and yet allowing it to remain in the center due to inertia. At the focal point inside this chamber, there's going to be a pea-sized pellet of deuterium tritium encased in a small plastic cylinder, blasted by lasers from all sides. Power from the lasers heat the cylinder and generate X-rays. Heat and radiation convert the pellet into plasma and compress it. During the final part of the implosion, the fuel core reaches 20 times the density of lead and ignites at about 100 million degrees Celsius. When the fuel is compressed enough and hot enough, fusion occurs. Again, getting it to that point is hard. The fusion reaction will be short-lived, about 1 millionth of a second, but will yield 50 to 100 times more energy than is needed to initiate the fusion reaction. So it seems pretty good so far. Once it ignites here, the thermonuclear burn spreads rapidly, many more times the input energy. Now, there's a problem, of course, and the problem is getting that to be self-sustaining. So some questions to think about here. Is this fission, fusion, or both? I'll let you go through this as a group or individually, and pause this and then move on to the next slide. So pause it, please. All right, once you've paused it, here are your answers. So induced by a slow-moving neutron, that's fission. Both have a mass defect. Fusion has stable byproducts. Transmutation, that's both of them. High temperatures, requires high temperatures, that's fusion. Creates high temperatures, that's both, but that's not a question here. Can produce neutrons as a byproduct, both. More energy per reaction, fission. More energy per nucleon, fusion. Lovely. Thank you.